Welcome! In today's session, we'll explore an interesting problem titled Number of Steps to Reduce a Number to Zero. This problem challenges us to systematically reduce a number to zero by applying a series of operations. We will break down the solution step by step, analyze its efficiency, and discuss key takeaways. Let's dive in. In this problem, you're asked to determine the number of steps required to reduce a given integer, number, to zero. The operations allowed are straightforward. If the number is even, you divide it by 2. If it's odd, you subtract 1. The goal is to repeatedly apply these operations until the number becomes 0 and count how many steps it takes. The input will always be an integer within the range of 0 to 10 to the power of 6, and the output should be a single integer representing the total number of steps required. Let's look at the first example to see how this process works. Here, the input is number equals 14. The output is 6, and here's why. First, since 14 is even, we divide it by 2, which gives us 7. Next, 7 is odd, so we subtract 1 to get 6. Then, 6 is even, so we divide it by 2, resulting in 3. Since 3 is odd, we subtract 1 to get 2. Now, 2 is even, so we divide it by 2 to get 1. Finally, 1 is odd, so we subtract 1 to reach 0. This sequence involves 6 steps in total to reduce 14 to 0. Now, for the second example, the input is number equals 8. The output here is 4. Here's the breakdown. Starting with 8, which is even, we divide it by 2 to get 4. Then, 4 is even, so we divide it by 2 again, resulting in 2. Next, 2 is even, so we divide it by 2 to get 1. Finally, since 1 is odd, we subtract 1 to reach 0. In this case, the total number of steps needed is 4. This demonstrates how the number of steps can vary depending on the input. For the third example, the input is number equals 123, and the output is 12. Here's the step-by-step explanation. Since 123 is odd, we subtract 1 to get 122. Then, 122 is even, so we divide it by 2 to get 61. Next, 61 is odd, so we subtract 1 to get 60. Since 60 is even, we divide it by 2 to get 30. From there, 30 is even, so we divide it by 2 again to get 15. Next, 15 is odd, so we subtract 1 to get 14. Then, 14 is even, so we divide it by 2 to get 7. From there, 7 is odd, so we subtract 1 to get 6. Since 6 is even, we divide it by 2 to get 3. Next, 3 is odd, so we subtract 1 to get 2. Then, 2 is even, so we divide it by 2 to get 1. Finally, 1 is odd, so we subtract 1 to reach 0. This entire process involves 12 steps to reduce 123 to 0. It's important to note the constraints and edge cases for this problem. The input number can range from 0 to 10 to the power of 6, so your solution must be efficient and handle large values within this range in a reasonable time frame. For example, if number equals 10⁻6, your algorithm should still compute the result efficiently. Additionally, consider edge cases like number equals 0, where no steps are needed and the output is 0, or number equals 1, which requires exactly 1 step to reduce it to 0. These constraints ensure that your solution is robust and performs well across all possible inputs. To solve this problem, we start by considering a brute force approach, which involves directly following the rules outlined in the problem statement. If the number is even, we divide it by 2, if it's odd, we subtract 1. This process continues until the number is reduced to 0. While this method is straightforward and easy to implement, it does not take advantage of any deeper insights or optimizations that could make the solution more efficient. Now, let's explore some key observations about the problem. First, dividing by 2 when the number is even reduces its value much faster compared to subtracting 1 when it's odd. This means division steps are more impactful in reducing the number. Second, the number of steps required to reduce the number to 0 is deeply tied to its binary representation. Each occurrence of the digit 1 in the binary form represents a subtraction operation, while the total number of binary digits, excluding the least significant bit, corresponds to division steps. These observations lead us to an optimized approach. Instead of focusing on simulating each step, we can calculate the total steps by summing the number of 1s in the binary representation for subtraction operations and the total number of binary digits for division steps. This insight forms the foundation of a more efficient solution. Using these observations, we can further optimize the solution by directly calculating the required steps based on the binary representation of the number. This avoids the need to simulate each operation step by step, making the process faster and more mathematical. Alternatively, we could stick with a simpler iterative or recursive approach to simulate the operations. While this method doesn't leverage the binary insights, it's easier to understand and implement. We ultimately chose the iterative approach for this problem. Here's why: it directly simulates the steps, making it intuitive and clear. Analyzing the binary representation is insightful but introduces additional complexity that may not be necessary in practice. The iterative approach strikes a balance between simplicity and efficiency, ensuring that the solution is easy to follow while maintaining optimal performance. Of course, there are trade-offs. Simulating the operation step by step ensures clarity and correctness, but it involves executing each operation explicitly. On the other hand, the binary approach skips explicit simulation but is less intuitive to implement. Regardless of the chosen strategy, both approaches share the same time complexity, which is O log number, as the number of steps corresponds to the number of bits in the binary representation. When it comes to space complexity, the iterative approach is very efficient, requiring only O1 space since it doesn't use any additional data structures. However, if we used the recursive approach, it would require O log number space due to the function call stack. Now, let's look at the final implementation of the iterative solution. The code is straightforward and follows the rules of the problem directly. We initialize a variable, steps, to 0 to keep track of the number of operations. Then, we use a while loop that continues as long as the number is greater than 0. Inside the loop, if the number is even, we divide it by 2, if it's odd, we subtract 1. After each operation, we increment the steps counter. Once the number becomes 0, we exit the loop and return the total number of steps. This implementation is clean, efficient, and easy to understand, making it a solid choice for solving the problem. The problem we're solving here is to reduce a given integer, n, to 0 using the minimum number of operations. The operations are simple: if the number is even, we divide it by 2. If the number is odd, we subtract 1. Our goal is to count how many of these operations it takes to bring n down to 0. To achieve this, we start by initializing a counter, called operations, with a value of 0. This counter will track the total number of steps taken. Then, we repeatedly process the number, checking whether it is even or odd. If it's even, we divide it by 2, and if it's odd, we subtract 1. After performing either operation, we increment the operations counter by 1. This process continues until the number becomes 0, ensuring we count every step along the way. Once the number n is reduced to 0, the loop terminates, and the algorithm returns the value of the operations counter. This number represents the minimum steps required to achieve the goal. A critical insight here is that even numbers are more efficient to handle because dividing by 2 significantly reduces their value. On the other hand, odd numbers require an additional subtraction to first convert them to even before division can be applied. This prioritization of dividing even numbers ensures that the reduction happens as quickly as possible. By following this approach, the algorithm guarantees that the number is reduced in the smallest possible number of steps, making it both simple and efficient. The algorithm relies on very basic data structures. Specifically, it uses 2 primitive variables, n, which stores the current number being processed, and operations, which tracks the total number of steps taken. No advanced data structures are needed because the problem is inherently linear and all computations are performed directly on the input. This simplicity leads to an efficient complexity profile. In terms of time complexity, the algorithm operates in O log n, because dividing by 2 repeatedly reduces the number exponentially. For space complexity, it is O1, since no additional memory is used apart from the 2 variables. This makes the solution both space and time efficient. When implementing this algorithm, it's important to consider several edge cases to ensure correctness. First, if the input n is 0, the algorithm immediately exits, returning 0 operations because no steps are needed. For very small numbers, such as n equals 1, only one subtraction is required, while for n equals 2, a single division suffices. Larger numbers that are powers of 2, such as 2k, are especially efficient to reduce, requiring exactly k divisions. For odd numbers, the algorithm handles them correctly by first subtracting 1 to make them even and then reducing them further through division. These edge cases highlight the robustness of the approach across a wide range of inputs. Let's go through an example to see how the algorithm works in practice. Consider the input n equals 14. We start with n equals 14 and operations equals 0. Since 14 is even, we divide it by 2, resulting in n equals 7 and incrementing operations to 1. Next, 7 is odd, so we subtract 1 to get n equals 6 and increase operations to 2. With n equals 6, which is even, we divide by 2 to get n equals 3 and increment operations to 3. Then, for n equals 3, which is odd, we subtract 1 to get n equals 2 and increase operations to 4. Now, n equals 2 is even, so we divide by 2 to get n equals 1 and increment operations to 5. Finally, with n equals 1, we subtract 1 to reach n equals 0, bringing the operations count to 6. Thus, the minimum steps for n equals 14 is 6. Similarly, for n equals 8, the process involves 3 divisions and 1 subtraction, resulting in a total of 4 operations. These examples illustrate how the algorithm consistently reduces numbers using the minimal number of steps. This Python implementation solves the problem of determining the number of steps needed to reduce a number to 0. Here's the detailed explanation. 1. Class definition and method name. The solution class contains the method number of steps, which accepts a single input number, representing the starting integer. 2. Initialization of step counter. We initialize a variable steps to 0. This will track the total number of operations performed. 3. While loop. To process the number, we use a while loop that continues as long as number 0. This ensures that we keep performing operations until the number becomes 0. 4. Conditional logic for operations. If the number is even, number %2 equals 0, we divide it by 2 using integer division, number // equals 2. If the number is odd, we subtract 1 from it, number equals 1. 5. Increment steps. After each operation, we increment the steps counter by 1. This keeps track of how many operations have been performed. 6. Return the result. Once the loop ends, i.e., when number becomes 0, we return the steps as the final result. ### key points. The algorithm efficiently reduces the number using the specified operations, ensuring minimal computational overhead. The loop runs in O log n time since the division by 2 operation reduces the number exponentially when it is even. Edge cases, such as number equals 0, where the loop does not execute and steps remains 0, are naturally handled by the implementation. This concise and straightforward solution ensures clarity, correctness, and optimal performance, adhering to the constraints and requirements of LeetCode problem number 1342. This is the Java implementation of LeetCode problem number 1342, number of steps to reduce a number to 0. The logic mirrors the Python implementation, where we repeatedly check if the number is even or odd, and perform the respective operation, dividing by 2 for even numbers and subtracting 1 for odd numbers. The steps are increment after each operation. Key differences include Java's explicit type declarations and the class-based structure. Let's start with the first example where the input number is 14. Initially, we have number equals 14 and steps equals 0. The goal is to reduce number to 0 while counting the number of steps. First, we check if 14 is even, and since it is, we divide it by 2, resulting in number equals 7. At this point, we increment the step count to 1. Next, we check if 7 is even, and since it isn't, we subtract 1, reducing number to 6 and increasing the step count to 2. Then, we examine 6, which is even, so we divide it by 2 to get number equals 3 and increment the steps to 3. For the next number, 3, we see that it's odd, so we subtract 1 to get number equals 2 and update the steps to 4. Finally, since 2 is even, we divide it by 2 to get number equals 1 and increment the steps to 5. Now, we move to the last step for this example. With number equals 1, we check if it's even, and since it isn't, we subtract 1 to reduce it to 0. This brings our total step count to 6. So, the final output for this example is steps equals 6. Moving to the next example, the input number is 8. Initially, number equals 8 and steps equals 0. We begin by checking if 8 is even, and since it is, we divide it by 2 to get number equals 4 and increment the step count to 1. Next, we examine 4, which is also even, so we divide it by 2 to get number equals 2 and update the steps to 2. Finally, since 2 is even, we divide it by 2 again to get number equals 1. At this point, we increment the steps to 3. Now with number equals 1, we check if it's even, and since it isn't, we subtract 1 to reduce it to 0. This brings the total step count to 4. The final output for this example is steps equals 4. For the third example, the input number is 123. Starting with number equals 123 and steps equals 0, we first check if 123 is even. Since it's odd, we subtract 1 to get number equals 122 and increment the steps to 1. Next, we check 122, which is even, so we divide it by 2 to get number equals 61 and increase the step count to 2. Then, we examine 61. Since it's odd, we subtract 1 to get number equals 60 and update the steps to 3. Now, we check 60, which is even, so we divide it by 2 to get number equals 30 and increment the steps to 4. Next, 30 is even, so we divide it by 2 to get number equals 15 and increase the steps to 5. For 15, since it's odd, we subtract 1 to get number equals 14 and update the steps to 6. At this point, reducing 14 to 0 follows the exact same steps as in example 1, which requires 6 additional steps. Adding these to our current count gives a total of 12 steps. Therefore, the final output for this example is steps equals 12. To analyze the time complexity of this problem, we need to focus on the two operations used to reduce the number to 0. When the number is even, we divide it by 2, which corresponds to removing one bit in its binary representation. This operation is logarithmic because the number of bits in a binary number decreases with each division. On the other hand, when the number is odd, we subtract 1, which flips the least significant bit from 1 to 0, effectively making the number even. The key insight here is that each operation, whether a division or subtraction, corresponds to processing one bit of the binary representation of number. Since the total number of bits in number is approximately proportional to log2 number, the time complexity of this process is determined by the number of bits, giving us a logarithmic time complexity of O log2 number. The space complexity of this algorithm is straightforward. We only need a single integer variable, steps, to track the total number of steps as we modify number in place. No additional data structures or memory allocations are required, making the space complexity constant, or O1. Now let's consider the best, average, and worst case scenarios. In the best case, where number is already 0, no operations are needed, resulting in O1 time complexity. In the worst case, for the largest possible value of number, such as near 2*3114 for a 32-bit integer, the number of steps depends on the number of bits in its binary representation, leading to O log2 number. The average case also falls into O log2 number, because the number of operations, on average, is similarly tied to the logarithmic growth of number. When comparing this optimized approach to a brute force strategy, the differences in efficiency become clear. A naive solution would involve repeatedly subtracting 1 from number until it reaches 0, regardless of whether the number is even or odd. This brute force method would require number steps, resulting in a time complexity of O number. In contrast, the optimized solution leverages the properties of even and odd numbers to reduce the number of operations significantly. By dividing even numbers and subtracting from odd numbers only when necessary, the number of steps becomes proportional to the number of bits in the binary representation of number. This brings the time complexity down to O log2 number. Mathematically, since each operation processes or modifies one bit in the binary representation, and there are approximately log2 number bits in total, the optimized approach achieves this logarithmic time complexity, which is a major improvement over the brute force method. Common mistakes can often be the difference between a correct solution and one that fails or produces errors. First, it's important to account for edge cases. For example, if the input number is 0 or 1, your code should handle these gracefully without causing errors. Testing boundary conditions ensures your solution is robust. Another common issue is infinite loops, often caused by incorrect or incomplete condition checks in your while loop. Always verify that your termination criteria are clear, ensuring the loop exits when the number becomes 0. Additionally, while brute force solutions can be a good starting point, they may lead to performance bottlenecks for large inputs. Instead, aim to refine your solution for better time complexity. Overcomplicating the logic is another pitfall. Introducing too many variables or unnecessary nested conditions can make your code harder to understand and debug. Lastly, don't ignore problem constraints. If the question specifies only positive integers, for example, make sure your solution adheres to these rules. Misreading constraints is a common mistake that can waste time and lead to incorrect outputs. Now, when approaching this problem in an interview, there are a few key strategies to keep in mind. First, take the time to fully understand the problem before diving into the code. Clarify the rules of the operation, like dividing by 2 for even numbers and subtracting 1 for odd numbers, and confirm any edge cases with your interviewer. Next, optimize your solution iteratively. While starting with a brute force approach is often acceptable, you should quickly propose and discuss optimizations, such as using bitwise operations like shifting bits for division by 2. Clear communication is also critical. Walk the interviewer through your thought process step by step as you code. This demonstrates your problem-solving ability and helps build rapport. Recognizing patterns can also give you an edge. Problems like this one, which involve having or reducing numbers, often have logarithmic solutions, so identifying this can help you converge on an efficient approach more quickly. Lastly, be aware of related problems that might offer helpful insights. For example, number of 1 bits involves bit manipulation, while power of 2 and counting bits both deal with halving and bitwise operations, which can inspire alternative strategies for this problem. There are several approaches to solving this problem, each with its own trade-offs. The brute force approach is straightforward. Simply follow the rules to iteratively reduce the number until it reaches 0. While this is easy to implement, it's not optimal for large inputs, as the time complexity can be O(n), where n is the number of steps. A more efficient alternative is using bitwise optimization. For instance, you can quickly check if a number is odd or even using n and 1 and divide by 2 using n1. This approach improves performance significantly but requires familiarity with bit manipulation. Another option is the recursive approach, which involves solving the problem by repeatedly calling the function with the updated state, such as f(n1) or f(n/2). While this can result in elegant and concise code, it risks stack overflow for very large inputs unless tail recursion is supported. Finally, you can leverage mathematical insights to skip redundant steps. For example, subtracting the largest odd component directly for large numbers can reduce the number of operations. This approach may require additional pre-computation or reasoning, but it can lead to significant improvements in efficiency. Each of these methods has its strengths and weaknesses, so choose the one that best fits the problem's constraints and performance requirements. Great job! To summarize, we solved the problem by breaking it into smaller operations and analyzing its efficiency. We discussed the solution's time and space complexity and highlighted the importance of recognizing patterns in numbers. Thank you for joining, and don't forget to like and subscribe for more coding content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!